Okay, hello everyone. Welcome both here in the room today and online on Zoom to today's event, today's workshop on neural networks for social scientists here in the MZES Social Science Data Lab. My name is Dennis Cohn, and I'm happy to introduce this event series to those of you who don't know it yet. The Social Science Data Lab is an event series here at the Mannheim Centre for European Social Research, where we provide a platform for researchers to present tools and methods for the collection, management, analysis, and visualization of social sciences. Our presenter today is Jack Collins, who is a PhD candidate here at the University of Mannheim and at the MZES. His research focuses on applied machine learning in conjunction with survey methodology. And before coming to Mannheim, Jack completed a master's in data science and worked as an IT consultant. His workshop today will provide an easy introduction to neural networks, which are machine learning algorithms that form the basis of many important technologies, including generative AI and computer vision. And I think this is the first in the sense that whereas usually we have tutorials on our blog Methods Bytes that build up on talks in the Social Science Data Lab, today we'll do it the other way around and actually have a complementary workshop on a tutorial on Methods Bytes that Jack authored earlier this year. A quick disclaimer, as we usually do, we are recording this live stream and we're doing so in active speaker mode, which means if you unmute yourself and speak, your audio will be recorded, and if your camera's on, your video will be recorded as well. You can ask us questions if you're live here in the room today, of course, by raising your hand and asking Jack whatever it is you want to ask. If you're online, you can either raise your hand in the Zoom chat or you can post your questions in the chat and we will read them out for you. That being said, Jack, thanks for being here today and the floor is yours.
Thanks very much, Dennis. All right. So, g'day everybody. So this is a beginner's guide to neural networks for social scientists. So why should social scientists care about neural networks? Why should you want to start to learn a little bit about neural networks? So neural networks are a very powerful and they're a very successful machine learning model. And if not everybody here is someone with a background in machine learning, that's okay. We're going to talk a little bit about what machine learning is along the way. But neural networks are a very powerful predictive model, and they've been very successful out in the world. Having said that, what's good about them is that they excel at complicated problems, and by complicated problems, I mean that there are deep interactions between the variables in your model. So that variable A has a certain effect, but only given that the value of variable B is such and such, or that variable C is such and such. When there are deep interactions between variables, neural networks are very powerful, and we're going to see that in action today. And then the other reason why you should care about neural networks is that understanding the basics of these kinds of very simple neural networks that we're going to cover today, that's a stepping stone towards understanding the more complex kinds of neural networks that underpin a lot of important technologies that we're working and looking at today. So once you understand neural networks, you're a very long way towards understanding convolutional neural networks, which are an extension of this, but those are specialized for image processing and computer vision. Once you understand neural networks, you can understand recurrent neural networks, which are one of the most successful algorithms for time series modeling. And also it's a building block of the transformer type architecture, which is what underpins ChatGPT that I'm sure we've all heard of, and all these other large language models. So one thing you're going to get out of this is once you understand neural networks, you're able to then take another step later to understand these more complex and very critical kinds of models. But today we're just going to cover the simplest kind of neural network that there is. And we're going to do a deep dive on that all the way down to the mathematics of how it works. We're going to step through that bit by bit. And by the end of it, you're going to understand the basics of what a neural network is, how they work, how you can apply one yourself. And a parting gift from me to you is that up on the Methods Bytes blog, is a link to some code that we're putting up. And this is a code artifact that you're welcome to use yourself. It's Python. And if you're thinking of maybe trying neural networks on your own research, this is a highly reusable class of code that you can throw into your own project and try and see whether neural networks are going to help you make good predictions in your own work. So we're going to try and approach neural networks, and this is normally something that is, in my experience, taught to people who are somewhere on like a second year or so of their data science or their computer science tertiary education. So to get this across for people who don't necessarily have that kind of background, I'm going to start with a little bit of a revision of things we might know already. So some of you might be a bit familiar with machine learning. Some of you might be a bit familiar with other kinds of predictive modeling. I'm going to start with a bit of a revision to sort of get everybody on the same basic level before we go on to more complicated things. So I'm going to start with, what is machine learning? And there's all kinds of answers to this question because there's all kinds of textbooks and so on written about machine learning. So rather than give you a textbook definition, I'm going to give you a definition of machine learning that's tailored towards helping today's workshop make a bit more sense. I'm going to, for now, give you the idea that machine learning is a model where data about cases go in and predictions about those cases come out. This could be putting in data of what we know at somebody at the time they are born and getting out a prediction of their lifelong income. It could be putting in meteorological data about today and getting out a prediction of whether it's going to rain tomorrow. Data goes in, predictions come out. So any machine learning algorithm can be expressed with this really simple function here, which is y hat. Does anyone know why it's got a hat over it? Yeah, go ahead.
Because it's a prediction and not, or estimate and not the actual value.
100% right, that's right. So there's going to be some true value of y out there, but y hat is our prediction or our estimate of the true value of y. How did we get y hat? Well, we took the data about the case and we threw it into some function f. What's the function? It could be all kinds of things. But the point is that you put data about the cases in and you get the prediction out. Okay. So I'm going to step through logistic regression. And a lot of us probably know logistic regression really, really well. So I'm going to go through that pretty quickly, but I promise that it's an important comparison point between neural networks, because as we're going to see, neural networks are, to quite an extent, they're actually built up of lots of little logistic regressions and functions that are similar to logistic regressions. So let's just quickly go over logistic regression, right? I think of logistic regression as happening in two parts, okay? So let's just imagine a scenario. This is the basic linear function. And a lot of us have probably seen this, but I'll break it down for anybody who's just maybe not a mathematics person at all. We've got our features x. You've got x1, x2, and so on and so forth until x, however many features you've got. So let's imagine that we're trying to build a model that's going to predict whether it's going to rain tomorrow. Okay, the thing that we're trying to predict is it going to rain tomorrow? And we could put data into our logistic regression, which is like, I don't know, maybe the air pressure today. Maybe x2 could be a binary variable for whether it rained today. Did it rain today? Yes, no. Okay, 0 for no, 1 for yes. And for each one of these features, we're going to multiply the value of that feature by a weight, by a magic number called W. How did we get this weight for each one of these features? We got it through trial and error, and we're going to talk about that a little bit later. But for now, just understand that we've got some magic numbers called W1, W2, W, so on and so forth, all the way through to N. And we're going to add all of these feature times weight pairings. We're going to multiply every feature by its corresponding weight. We're going to add them all together, And then at the end of that, we're going to add another number called beta. Sometimes it's called the intercept. And we're going to add that magic number to it. Again, that's a magic number that I got through trial and error. But for now, just understand that I have this magic number, beta. And I'm going to add it to the sum of all of these feature and weight pairs. And I'm going to get another number called G. And G by itself doesn't do anything yet. It's just a number. But here's the thing to understand about G. As the value of one of our features gets bigger or smaller, any one of our features gets bigger or smaller, G is also going to get bigger or smaller. So let's just say that over here, we've got X1 and W1. If W1's a positive number, the more of X1 I've got, the bigger G is going to get. And if W1 is a negative number, then the more of X1 I have, the smaller G is going to get. So each one of my values in here, my X1, my X2, my X3, when they change, G is going to change. G is going to go up or down. Okay. So G is just this number that goes up or down depending on the sum of all of these values or the sum of all of these weights. Okay. What do we do with G? We're going to plug it into this thing here, which is called a sigmoid function. And what a sigmoid function does is if you've got a number that is very positive, it's very high above 0, the sigmoid function is going to approach 1. So when the more positive your number, the closer the output is going to be to 1. When you've got a very negative number, when G is very negative, it's going to output a 0. And if G just happened to be 0, then the output of your sigmoid function would be 0.5. Okay. And you can interpret these as probabilities. So 1 is, I am 100% sure it's going to rain tomorrow. 0 is, it's definitely not going to rain tomorrow. And 0.5 is, no idea. There's a 50-50 chance that it's going to rain tomorrow or not. The model has no idea. So that was a really quick run through of logistic regression. Normally there's a whole lecture for that sort of thing, but we've run through it very quickly. Is this, how is the room, and I mean the physical room in front of me because I can't visually gauge the Zoom room, but is this is all pretty well understood, right? Okay, I just wanted to go over this because we're going to be seeing these functions a lot when we go to our neural network. No, is that okay, Dennis? Yep. All right. So I'm going to start to turn now to why neural networks are good for certain circumstances, and they make it's good to compare them to logistic regression. So before I move on from this, I just want to get across this idea that there's a particular value of G, and when G goes above that value, you're going to classify your case one way. Your logistic regression is going to output a 1. And if G falls below a certain threshold, the logistic regression is going to output a 0. Okay, so there's a kind of, you can imagine that somewhere there's this threshold for G, at which the output of the logistic regression is going to flip. And I can represent that in this diagram here on the left. So what are neural networks good for? They're good for non-linearly separable problems. So we're going to break down what's a non-linearly separable problem, okay? A linearly separable problem is what logistic regressions are actually, a lot of the time, really good for. So what if I had two features? I have X1 and I have X2, and they're just these theoretical variables that I'm going to put into my logistic regression. And when the combined value of X1 and X2 times their weights plus their intercept is above a certain value, I'm going to predict that this dot is blue. And if it's below that value, I'm going to predict that it's red. And here in my nice little example, you see that I could build a really good logistic regression model for this linearly separable problem. Because if I know the value of X1 and I know the value of X2, I'm going to guess right, pretty much 100% of the time, whether the dot is blue or red. Now, I've made a little bit of a jump because I've showed you this logistic regression diagram, and now I'm showing you this diagram. But is everybody following so far how we got from the logistic regression diagram to this? Yeah? Okay. Okay. But, and But over here on the right, we've got a non-linearly separable problem. And you can see that there's just no way that I can draw a line that would separate the blue and the red dots, okay? Now, a lot of you probably know things like, there's polynomial functions, right? So we don't just have to have a straight line, we could have a polynomial function and we could add some curves to this line. But there's no way I can make a curvy line that's going to perfectly encapsulate this circle of dots in the middle, okay? Some of you who are probably way too advanced to be in a beginner's guide to neural networks know that you actually can get logistic regressions to handle these kinds of problems. You just add a whole lot of interaction terms to your logistic regression, but that requires you to sort of explicitly tell your logistic regression that you want to handle some interaction. So I want to just get across the idea that what makes a non-linearly separable problem is that each one of these features doesn't just have one effect, okay? So over here in our linearly separable problem, the more of x2 you have, the more likely it is that you've got a blue dot. The more of x1 you've got, the more likely it is that you've got a blue dot, okay? But over in our non-linearly separable problem, it's not that simple. It's a little bit more like the dot is going to be blue if the value of x2 is in this range and the value of x1 is in this range. But if the value of x2 is in this range and the value of x1 is in this range, then the dot's going to be red. So that's an example of a feature interaction, that the effect of one variable depends on the value of another variable. Okay, logistic regressions aren't really well suited to this problem. Again, there are things you can do. You can actually build into your logistic regression this explicit logic. You can actually explicitly write into your logistic regression function, hey, logistic regression, take into account these various scenarios, but you have to explicitly know what features are going to interact with what, okay? And we're going to see that a neural network, you don't need to explicitly tell it, hey, I think there are interactions between two features. The neural network will actually just work it out. And let's actually do a demonstration. So we're going to come back to this and we're going to talk about this in detail, but this is something called TensorFlow Playground. It's a very nice resource for visualizing what's happening inside a very simple neural network, and it's a nice teaching tool to get the intuition. So you're welcome to take a look at this yourself. We're going to come back to this a little bit and talk about it in detail. But for now, I just want you to notice this thing over to the right, which is this problem that we talked about before, where there's no way you can draw a line to separate the orange and the blue dots, okay? But we're about to just execute a neural network that's going to make a classifier to classify whether the dot's blue or orange. So here it goes. Whoop. And, oh, it's very slow because the browser is just slow. There we go. So it's done. So we're gonna crack into this. We're gonna look into the detail of this, but I just want to show you that this is an example of a neural network accomplishing exactly this problem, and it did it in a few seconds, where we can actually create a function, just like our logistic regression was just a function, but we can create a function that can output predictions. Given a certain horizontal and vertical coordinate, predict whether the dot is going to be blue or going to be orange. And this is what we're seeing over here on the right, that our neural network would classify a dot that's in that particular region orange or blue. And you can see that it's really correct about that it's able to separate the blue and the orange dots really, really well. Okay. So that is the concept of what we're doing here, okay? Neural networks are good at solving these non-linearly separable problems, whereas other models like logistic regression would struggle with that sort of thing. So we're going to start to go into the math. So how are we all feeling before we start to go take a look at network diagrams and equations, and we're about to get a lot more mathematical. Okay, you ready? All right. I'm going to jump back into presenter mode, and I'm going to put this up here again. Should I? No? Okay. 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 I'd sort of like to get rid of that. There we go. I think that's okay, isn't it? All right. I think that's as good as we can do. Okay. So we're going to step through an applied example. We're going to step through a neural network applied example. And then at the end of that, I'm going to introduce the equation that expresses a neural network in one equation. So a lot of you who have done any machine learning stuff have probably seen this example before. This is a famous example machine learning data set. But what we're trying to do is we're going to predict what subspecies of iris flower a given specimen is based on measurements of its petals and its sepals, which is this other kind of little petal-looking thing over here. I'll be honest, I've never heard the word sepal before looking at this data set. But okay, so we've got, for each, we've got a data set of, I think it's like 1,000 or something, iris flowers, and they're all of different subspecies. And we have measures of their petals and their sepals. So we've got the width and length of the petals and the sepals. So 4 features. And we're going to guess what subspecies of iris flower it is based on those measurements. Okay. So let's step through what the neural network is doing. So this is where you can see the network part of the neural network. So neural networks are based on this graph and node, this node and edge data structure like this, okay? And we're going to step through what all of this means in a moment. So I have my 4 features here: width, length, and these are just any float. So this is, 3.4, 2.5, 1.6, whatever, okay? And all 4 of these numbers are going to be sent as input to each one of these 12 nodes here. So just imagine these 4 numbers being sent as input to each one of these 12 nodes. So what does the node do with it once it has those 4 numbers, those 4 inputs? And by the way, this is where the neuron part of the neural network comes in, because in the terminology, we call each one of these nodes a neuron. And we're going to show you why it's called a neuron in a moment. So our 4 measurements, sepal width, sepal length, petal width, petal length, all 4 of those numbers have gone into neuron number 1. What's neuron number 1 going to do with it? Well, it's actually going to do basically a logistic regression is what it's going to do with it. It's just going to take each one of those numbers. X1 could be sepal width. The next 2 could be sepal length. It's going to multiply each one of those by a corresponding weight that we have just for that feature. We're going to add it all together, and we're going to add a bias, and we're going to get our value G. We're going to throw it into a sigmoid function. And then this node, neuron number 1, is going to output a number between 0 and 1. And that's going to be the output of our sigmoid function over here. And each one of these 12 neurons are all going to do the same thing. But each one of these 12 neurons is going to have slightly different weights and a slightly different bias in each neuron. So it's going to output a number that's between 0 and 1, but a slightly different number, each one of these 12 neurons, okay? What's it going to do with those 12 numbers? Well, all 12 of those outputted numbers are going to go into each one of the neurons in this second layer of neurons. And in terminology, we call this a layer. We call it a layer of neurons. So all 12 of the outputs from this first layer are going to go into each one of these 12 neurons in this second layer. And then in that second layer, we're going to do another of these functions, just like a logistic regression. Okay. And in each one of those 12 neurons is again going to output a number. And it's going to go into, all 12 of those numbers are going to go into each one of these 3 neurons over here. And we call these the output nodes. This is the output layer. This is where we're going to get our output. And it has 3 neurons in it because we have 3 outputs that we're interested in. It's the probability that the flower is a setosa, the probability that it is a versicolor, or the probability that it is a vaginacea. And again, in each one of these output nodes, we've still just got another one of these logistic regression looking functions that's going to output a number between 0 and 1. And in the end, we're going to get these numbers for a given flower that we inputted, okay? And if we do that 100 times, we're going to get 100 predictions for 100 flowers. So what I did was I built exactly the model that you're seeing here. I trained the model on, I think it was maybe 500 or something flowers. And what does training mean? Training is where we figure out all of the weight values that we should have. So all of these weight values and all of these bias values, how do we figure out what the best weight and the best bias is that we should use? We do it by trial and error. And we're going to get a little bit into how that trial and error fitting process works in a bit. But for now, just understand that we take some historical data and we put it through the model and we just guess what the weights are and we get out some predictions, and those predictions are terrible. But then we nudge the weights around and then we get some maybe slightly better predictions. And then we keep doing this until we get the best predictions that we can figure out how to get. So we train our model and then we make some predictions with some new data. And this is how my model did. So this is a confusion matrix. Is there anyone who hasn't seen a confusion matrix before? Right? Everybody's seen a confusion matrix, yeah? Okay, all right. So you can see that the model did extremely, extremely well, right? It only misclassified one of the cases, okay? We just have one case where we predicted that the flower was a versicolor, but it was actually a vaginacea. But other than that, it predicted all of these cases perfectly well. So just before we move on, let me give you a bit of terminology. Okay, so let me formalize everything that we just stepped through as a function. So let's express everything that we just talked about, but in math. So firstly, I want to say that we just talked about all of these sigmoid functions. We said that every time some input goes into a neuron, the input is going to go into a sigmoid function. But in reality, it doesn't have to be a sigmoid function, right? Actually, all we want is a function that is going to do something like what a sigmoid function does, which is where if it's given a certain input that's above a certain threshold, it's going to do one thing. And if it's below a certain threshold, it's going to do another. Now, a sigmoid function works like that because if the input is very positive, it's going to output a 1. And if the input is very negative, it's going to output a 0. But there's other functions, not just the sigmoid function, but we've got other functions. So for example, tan H will output a -1 if the input is very negative, instead of a 0 like the sigmoid function does. Rel U is another popular one. If the input is below a certain threshold, rel U will output a 0, and if it's above that threshold, it will output the value of G, the value of that linear function that we looked at before. So there's lots of options, not just a sigmoid function, but you've got lots of options for what's called your activation function. What's the best activation function to use? There's no before the fact way of deciding what the best activation function is. Rather, we trial and error. Again, we trial and error what the best what activation function we should use and see what gets us the best results. So here is our neural network that we talked about just before, expressed as a function. Okay, so y hat, our predicted y, equals the activation function as applied to all these matrices, matrix operations. So WL is an array of weights. No, that's wrong. Sorry, it's a matrix of weights. Sorry. WL is a matrix of weights, and it corresponds to, let's say it has 12 rows because we have 12 neurons, and it has 4 columns because we have 4 inputs in this first layer, and we're going to multiply it by XL. We're going to multiply it by the XL of the previous layer. So in the case of dense layer number 1, the previous layer is the input layer. And XL is an array of these 4 inputs. So we're going to multiply our 12 by 4 matrix WL by our array of 4 items, XL minus 1. And that's the same thing as stepping through all of these neurons and multiplying them by all of these inputs. So we're going to end up with a matrix which is 12 by 4, which is the product of WL and XL minus 1. And then we're going to add beta L, which is all of the intercepts, all of the beta terms in all of these neurons. And from that, we're going to get an array of 12 numbers, which is the output of, which is the G value in each of these nodes. And then we're going to apply an activation function to all of those 12 items in our array. And that is going to be the output of this layer. So that would be XL. And then we're going to repeat that for the next layer. So now this XL, which is the output of this first layer, is then going to be plugged into the same function again for the dense layer number 2. And this is going to go on all the way through until we get to the very last layer, which is our output layer. And then that's going to output an array of 3 items, which are the 3 probabilities: is setosa, is versicolor, is vigidicea. So that's the math of a neural network. And actually, I should specify that this is called a fully connected neural network. This is called a feed-forward, fully connected neural network. And it's called a fully connected neural network because every neuron is going to be input, every neuron in every layer is going to be input for every neuron in every subsequent layer. One way we could vary this architecture is that we could make it so that not every neuron is input into every other layer. We could actually just pick some of these random connections between neurons and we could cut them, right? We could cut the connection and we could just not let that neuron put input into that other neuron. Then it would no longer be a fully connected neural network. But just for now, we're just talking about fully connected neural networks. So I'm just going to pause for a second and just stop because we've just absorbed a whole lot of math and a whole lot of calculations. But is this okay for everybody? Is this easy enough to follow so far, how we arrived at this function to describe our neural networks? Yeah? Yeah? Big nods, all right. Okay. The other technical matter that I want to get across is how we actually get all of these weights and these biases for our neural networks. So I mentioned before that it was trial and error, and that's true, but if it was really just random trial and error, it would take us forever to find the right weights, right? Because there's literally infinite numbers that you could be trialing for each one of those weights. And if you were really just blindly guessing all of the weights and biases to put across my whole neural network, it would take a computer, forever to work this out by pure trial and error. So it is trial and error, but there's a little bit of a process to make sure that we're making guesses at what the weight should be as efficiently as possible. And this is where we get into something that you're going to hear about and something that you're going to have to discuss and talk about if you actually use neural networks in your own work. We're going to have to talk about gradient descent. So those of you who are familiar with Monte Carlos will probably have a really easy way to intuitively understand gradient descents right away. But here in my hypothetical scenario, I've got a model that's only got two weights, theta 0 and theta 1. I've only got two weights, and I need to find the value for those two weights that's going to get me the best results. And results, we always measure in machine learning through something we call the loss, right? Which is just another way of saying error. But for any model, you've got how well it performed versus you've got the predictions that it outputted, and then you've got the actual value. And then in some way, you can compare the actual values with your predictions, and you can come up with some measure for how well you think it did. So that could be how accurate the predictions were. If it's a regression, that means that we're estimating a continuous variable. It could be how far off your guess was from the actual value. Okay. So we've got what's called our loss, and we want to minimize error, or we want to minimize loss. So we can create a graph like this, which is where I'm trialing all of these values of my two weights, theta 1 and theta 0. And then I'm on this depth axis, this third dimension, I'm plotting my loss, my error. And I want to tune my weights to be at the value that had the least loss, that had the least error, okay? But how I find that by random trial and error is, okay, at first, I just start with a random value and I get a certain loss. And then I could try every value for my two weights that are within a certain range in the immediate area around my starting values. And some of those values are going to be better and some of those are going to be worse. And I can move my weights in the direction that it was better, that it had lower loss, okay? So I can then repeat that process at another step out at another point, and then I can move in the direction that things were better, okay? And so this is why it's called gradient descent, because we're moving through, we're treating it like a space, and we're moving through our space in the direction that we seem to be getting lower and lower loss values. Now, here's a problem. Does anyone know what the local area minimum problem is? So local area minimum problem is a problem with gradient descent that over here, you've got this another area that's pretty low. But let's imagine that this area over here was actually lower than this area. So we did our gradient descent. We started up here, and then we just did our process of taking a look in our immediate area and trying to find which had the lower the lower loss. And we just eventually did this walk. We did this walk and we eventually found this low point. Okay. And once we've hit this low point, every change in the weights in the immediate area is only going to take us higher. It's only going to cause more loss, right? So our little agent here that's walked all the way down to here, there's no direction they can move. That's not going to move them up. But what if this area over here was actually lower than this one over here? Our little random walker here would never get there, would never arrive there if it only looked at the area around it. So that's called the local area minimum problem. It's found an area that's as low as it can find in its immediate area, but it's not the lowest one that potentially exists. So something gradient descent algorithms try to do is they also from time to time throw out random jumps. So instead of varying our weights only by a little bit in our immediate area, we vary our weights by a lot randomly, just to see whether there could be some other spot in this space that could actually have been lower, and we didn't discover it because of the local area minimum problem. And then the other thing that I want to talk to you about is something called backpropagation. Backpropagation is something that neural networks do specifically, and it is where over here in our neural network, our guess, when we're training our neural network, these guesses for is setosa, is versicolor, is virginacea could be wrong by a certain amount. So we can actually quantify how bad our guesses are, but we can also take a look at which neurons are actually driving those bad guesses. And then we can actually target those neurons, the neurons that are causing our guesses to be bad, and we can actually adjust the weights in those specific neurons. Instead of trying to just randomly tune the weights across all of the neurons. So we won't go too much into that, but just understand that backpropagation and gradient descent are these two algorithms that neural networks use to discover the best weights and biases to use. And it's designed to be more efficient than just totally randomly guessing all of these values. And that's important because the range of values that your neural network has to do gradient descent for, or has to do propagation for, is going to affect how long it takes to fit and to train your neural network. Okay, we are going to go back to our TensorFlow playground, and we're going to talk about, so now that we've got the basis of the math for the neural networks, that you've stepped through the equations and you've stepped through the concept of gradient descent, let's actually take a look at what are these neurons in these layers doing. So we talked about the math of the neurons in the layers, but what do these neurons in these layers actually do intuitively? And I'm going to demonstrate the benefit of having more or less neurons in your neural network. And how I'm going to do that is I'm going to go back to our example from before, where our neural network that's just got, it's got 4 neurons in this middle layer here. And here's a little terminology alert. This first layer is called the input layer. This last layer is called the output layer. And any layer that you have in between the input and the output layer is called a hidden layer. That's just a bit of terminology. They're called hidden layers, just so you know. So here we have our input layer. We've got 4 neurons in our first hidden layer, 2 neurons in our second hidden layer, and then they go into the output layer. Okay, so that's our architecture, and it apparently works really, really well for this problem. But what if we gave it a more complicated problem? So what's more complicated about this problem is that there's way more feature interactions, right? Previously, we just had to say, if the vertical axis falls between this range and the horizontal axis falls between this range, make it blue, otherwise make it orange, you could say, okay? But in this more complicated example, there are way more layers to that you're going to need. It's more like, when the value of the horizontal axis is such and such, but the value of the vertical axis is this, but not this, but this, but not this, then it's going to be a blue dot or an orange dot. So there's deeper feature interactions. And so I'm just going to hit play. So this is the same neural network architecture that we had before, but it's got a more complicated problem. So we're going to take a look at how it does. Okay. And by the way, the previous neural network had totally solved the problem by now. While we're looking at it do this, I'm just going to talk about this number up here called the epoch. The epoch is one set of random weights and biases that we tried. Okay, so we tried a bunch of random weights and biases. We checked the loss, and then we tried another set of random weights and biases, and then we checked the loss of that. And you can actually see the loss graphed out over here on the right. And this is showing how it's gradually, as it tries more epochs, as it tries more weights and biases, and then does its gradient descent, it's gradually getting less and less loss, okay? But you can still see that the loss is still pretty high. It's doing pretty lousy, right? It's misclassifying all of these blue dots over here. It's misclassifying all these orange dots over here. And we've let it run for 600 epochs and it's just not getting any better, right? Whereas the other one was in the other problem, this same neural network had solved the problem really, really quickly. Okay, so, oh, didn't mean to do that. Yes.
So test loss is high, is good.
Yeah.
The other way around. Like,
No, thanks for pointing that out. Let me explain that. So I'll start back at what train and test is. You see all these dots here? We're going to randomly grab half of them, and those are our training dots. Those are the ones that we're going to train the network on. The other half that we didn't train, we're going to hold them away from the network, and then we're going to use those to make predictions. And what we really care about is how good the predictions were on the test set. Because the test data was data that the neural network didn't see when it was training. So in general, all models will have, or unless something is going really, really wrong with your model, the training loss should always be pretty low because that's the data that the model actually got to do its gradient descent on. But the test loss, the error in the test set will always be a bit high because that was data that it didn't see. But we always want our models to be able to make good predictions about data that it didn't have access to when it was training. So the test loss being higher, it should always be higher, but the test loss is what we really care about. The training loss is kind of just a bit of an indication. Does that make sense? Right.
I just want that number to go to zero, basically.
Ideal, if test loss was zero, then you'd have like a perfect classifier and it would be misclassifying 0 dots, and that would be exactly what we want ideally. Okay, so why didn't this neural network architecture work for this problem when it worked so well for the other problem? And like I said, the main difference between these two problems is that there are deeper levels of interactions going on between our two variables. Those two variables being the vertical axis and the horizontal axis value. So let's actually step through this visualization of what's going on in these neurons. So in this neuron, we've got a activation function and our two inputs, the vertical axis and the horizontal axis values. They're going into each one of these 4 nodes. And in each one of these 4 nodes, we're doing our linear function that combines all those values, adds a bias, and then puts it through an activation function. And then out of the activation function, our activation function is going to say, if it's above this threshold, I guess that it's blue. And if it's below this threshold, I guess that it's, sorry, let me rephrase that. The activation function is going to output a 1 if the output of its linear equation is above this threshold, and it's going to output a -1 if the output is below that threshold. And you can see that in each one of these neurons, it's got a slightly different threshold. It's making some slightly different thresholds, past which it's going to output a -1 or a 1. And then these numbers, which are -1 or 1, are then going to go over here to this other neuron. Actually, tell you what, it's even better if I do it like this. Let's just go back to our problem that we solved before, okay? Random 4 different thresholds past which it's going to output -1 or 1. Neural network outputs these -1 or 1 numbers, goes to this next layer. And now you start to see that the threshold is curved, okay? What happened here is that these neurons, these linear functions in these preceding neurons, introduce degrees of freedom to create these curves in this subsequent neuron. And this one also has some curves. And when you put those 2 curved decision boundaries into another one, you can actually get the full circle, okay? So what's going to help us do this is that we have some more neurons. And then the second, so more neurons is going to allow us to trial more of these thresholds, to include some more of these thresholds. And then the layers are going to introduce the ability to have those as degrees of freedom, okay, in our curves, in our final decision thresholds. So I'm just going to go ahead and bomb this with just tons and tons of neurons. Add a couple more layers, why not? But the point is we're giving the network more degrees of freedom through which to create these more, these finer separations of the space. Get that? And you can kind of see that, you might not have noticed this, but that epoch number is going up a lot more slowly now. It's going up a lot more slowly because it takes longer to do one round of training, because it's got more computations to do, because it's got more neurons and more layers. I guess this could take a while. So while we're waiting for that, I've got to say this was a little quicker on my own laptop. But while we wait for this to do its fitting, do we have any questions so far? Yes.
So you're trading efficiency for accuracy, right? Is there any other downside to introducing more neurons?
That's a really good question. Okay. So the reason we don't just introduce as many neurons and layers as possible is overfitting. So do we all familiar with the idea of overfitting a model, right? The short answer is that actually more neurons and more layers will tend to overfit. And this is why actually simpler models, including logistic regression, often have better validation scores, better test scores than neural networks, for the simple reason that if your problem is linearly separable and it's fairly straightforward, a linear model like a logistic regression will probably do better than a big complicated neural network, because the neural network, it's very difficult to stop it from overfitting.
Makes sense.
So this is coming along now. It's not even at its best as it's going to get, but you can see that it's actually started to subdivide things pretty well, and that it's actually got a much less, here you go. So what's happening here is really interesting. Remember that we said that when your gradient descent algorithm reaches a certain point, it hits a local area minimum. These algorithms will try to just randomly, totally throw out like really random values for the weights to see whether it's getting stuck in a local area minimum. And that's exactly what it's done, right? So it was doing gradient descent, getting to a certain point, and then it just tried some random weights, and then it found that actually it could get to a lower level of loss if it tried some totally random other weights, and it did. And because it found it broke out of a local area minimum in its gradient descent problem, it actually discovered another region in that space to explore and to find some totally different set of weights. And that's why the training and test loss have gone like this. And that's why they're suddenly, after they've gone up and down so furiously, they've come down to a much lower level of loss. So that's what's happening inside our gradient descent algorithm. But you can see now it's doing really, really well, right? I don't think it is, you know what? It is misclassifying about this one unfortunate blue dot here. But I have to say that's probably because there's just, not enough other blue dots around it, that it probably just got, this was probably only in the test set. But that's an example of overfitting, right? That if it was, you would ideally have it so that it it has blue through here, but it's kind of overfitted to say, well, there's no orange dots in that area. There's no orange dots, sorry, blue dots in this area. So I'm going to guess that it's orange. Okay. And you can see that it did another round of throwing out random values to see whether it could break out of its local area minimum. But it didn't really save as much loss as last time. So I'm going to leave it there at almost 900 repetitions of the training process. But yeah, now you can see that with these more neurons and these more layers, it actually adds more degrees of freedom so that it's able to fit to a more complicated problem. And that is it for the learning for today. I'm just going to close off with a little parting gift from me to you. Over on the Methods Byte blog, we've written an article about how you can implement artificial neural networks yourself. It's all in Python. But in there, we've got this article that steps it through, but also we have a public GitHub repository. In that GitHub repository, I'll share it now. In that GitHub repository is a Jupyter notebook. In that Jupyter notebook is an example class. So let's go to it now. Artificial neural network hypermodel. What does this class do? This class lets you say, here is a range of numbers of neurons, a range of numbers of layers, and a bunch of different activation functions that I want to play around with. Here's my data. I'm going to input that into this model, and it is going to output the best of those models that it could find. So previously we had to manually play around with the number of layers and the number of neurons. Here is a class that will that will do all of that exploration automatically for you and explore through your data and find, you know, the best possible set of neurons and layers. And so the notebook steps you through how you can apply this to regression problems, to binary classification problems, multi-class classification problems. And if you're willing to learn a bit more about the coding, you can actually easily extend this model to do recurrent neural networks, to do convolutional neural networks, and work on images and time series problems and so on. But that's in the article, and we'll let the article stand for itself. So what did we learn in this? Why did we do this today? So this is about communicating the intuition for why neural networks are better for certain problems. What kinds of problems neural networks are well suited to. We did a deep dive onto the mathematics of these basic kinds of neural networks. And the reason it's good to understand these very basic kinds of neural networks is because it's a stepping stone to understanding more complicated kinds of neural networks. So there is recurrent neural networks for time series problems. There's convolutional neural networks for image processing. There's transformer architectures for large language models. But all of these have the neural networks as their basic building block. So that's it for today. And we can open it up to questions, comments, generally chatting. Otherwise, if no one's got anything, we can hand it over to Dennis.
Yeah, I mean, I get the intuition now.
Yeah.
Can you tell us about an application in research?
Sure. Yeah. So I guess the one that's on my mind the most clearly would be my own dissertation work at the moment. So I'm currently working with what am I? So my dissertation project is around panel surveys or longitudinal surveys, specifically with the GESIS panel. And we want to know whether we can use neural networks to predict who is going to non-respond in a given wave. So we've got all of this data about people, right? We've got all of this data from their recruitment interview. We've got all the data that they give us when they fill out every survey. and we want to know whether we can predict whether they're going to be one of the 5%, I think it is, of people out of the 5,000 people we invite every 3 months, which one is going to be the person who doesn't respond that particular wave. And I'm looking at recurrent neural networks, which are an extension of these kinds of neural networks, and without getting into the deep sort of mathematics of it, but basically you, instead of inputting a single value like we inputted sepal width, sepal length, etc., and those are just single numbers, you can input an array of numbers, and the neural network, and that array of numbers can be any length whatsoever. And you can input that into the model, and the model will recursively update its predictions for each time step that you gave it. And this we're interested in because, well, panel data is time series data, right? So the idea is, could you just input the time series of these values, and would you be able to get some more information out of, would that then improve the predictions? And the reason it might improve the predictions is if you have complex temporal dependencies. So we talked about how neural networks are good for problems where one feature is interactive with another feature, it depends on another feature, depends on another feature. In a recurrent neural network, you can do the same thing, but it's about temporal dependencies. So a recent value could depend on what your value was at a previous time step, and again, at another previous time step, at another previous time step, so on and so forth. And recurrent neural networks can handle fitting to those temporal dependencies. So those are just the neural networks that I'm fitting, now basically, and they're working quite well, I think. So yeah, sorry, is that an okay example of a application of it, or?
Yeah, absolutely. And what kind of is the output then? Like, do you get like predictions for every single individual that is still in the survey?
Yeah.
Whether the individual will drop out in the next one?
Yeah, exactly. So like for any given wave, we can take everybody who we invite to that wave, and then we can plug in what we know about them, beforehand, and then put that data in there, and then we make it a binary classification problem, right? One for, positive for they do drop out, negative for they don't drop out, non-respond. So then the model just outputs a number which represents the probability, the estimated probability, right? 70% chance that this one's going to drop out, 20% chance that this one's going to drop out, that kind of thing. But yes, and it's for each participant. Yeah.
Kind of like also the last step. Now, if you know these risks for each individual, is it still possible with those neural networks to get back at any kind of predictor, or is this just the black box and you take that value as given? And that's
cool. Yeah. So you brought up a hot topic keyword, the black box. So we're getting at the idea. So like, again, it's good to compare these things to logistic regressions, right? So in logistic regressions are really easy to interpret because each variable has a weight, and then you can use that weight to say, to make statements like, if it rained today, the probability that it rains tomorrow is going to increase by a certain amount, because that's actually what you can crack out from the logistic regression. Neural networks, and not just neural networks, but any model that sort of automatically takes into account interaction effects like this. So tree-based models and random forest models and extreme gradient boosting models, for example, those are also kinds of models that automatically fit to these deep dependencies in things. And therefore you can't just as easily say what the effect of a given an increase in a quantity of a given variable will have this effect, because actually its effect depends on this, that, and the other thing, right? So this is where we have to get into ideas about how you interpret these models. One of the most common ways, and I'm not saying it's the best way, but it's probably one of the most common, is what's called permutational feature importance. And permutational feature importance is where we have our trained model, right? Okay, so we've got our special function that we put data into it and we get predictions out. Okay, what we're going to do is we're going to put data into it to get some predictions, but we're going to take one of the features in that data and we're going to scramble it. We're going to, in some way, make it useless. We're going to replace it with white noise. We're going to just like take people's values and just scramble them around. And what that's going to do is it's going to mean that the value of that particular feature is actually just nonsense. And then we're going to see how much worse the predictions got when we made that feature essentially unavailable to the model. And so that's why we call it the importance of the feature. So the permutational feature importance is the loss that we got when we excluded that feature from the model. And this way, if the predicted performance drops a lot when that particular feature is withheld, then we can say that that's a really important feature, because without it, the model just didn't do very well. But that doesn't tell us the direction of the impact, right? It doesn't tell us whether more of this of variable A is going to lead to more of the outcome. It just tells you how important how much predictive power that feature has. Getting into things like saying, I've got a neural network, now tell me, if I have more of value A, what's going to happen, is still really hard. There's things that you can go look up, like SHAP values, for example. So that's one way of trying to look into these effects. But yeah, interpretive machine learning is a whole other thing. Please.
Thanks, Jack, for this very accessible introduction to the neural network. Following up on Manuel's question, I was wondering, in your machine learning toolbox, you mentioned logistic regression as a very simple way of doing it. Where do neural networks stand? Is that, I guess, a rather complex model, like after trying these tree-based approaches that you would apply? Or is it somewhere in between, or like what are your decisions in your own work?
Okay, I've never tried to like rank them by complexity. So I usually just think of them as they're linear or they're non-linear, and by non-linear I'm mostly thinking about the fact that they take into account interaction effects automatically. Linear models can still take into account interaction effects. You just have to explicitly build them in. So yeah, logistic regression we usually say is like one of the simplest kinds of machine learning models out there. And tree-based models, this isn't a beginner's introduction to tree-based models for social scientists, so we're not talking too much about that today, but they can also do this interaction effect. Okay, then why ever use neural networks? Why not always use tree-based models? A short answer to that is that neural networks can create finer densities of probabilities in some of these spaces. So you can see here that we've got these areas that are really blue, areas that are really orange, and then you've got these areas that are white in between, that are the basically 50-50, not sure which one to classify it as spaces. Tree-based models basically would take this space and basically create squares, basically just cut this up into squares. And it can have really, really small squares and really, really big squares, but it's cutting it up into squares. Neural networks can actually create finer spatial separations, in a word. So that makes neural networks better for more complicated problems where that's a good thing, but it also makes it really hard to avoid overfitting. Because it could be good that you don't too finely discern cases. It could be good that you let things be a little more general because maybe that generalizes a little bit better. So yeah, sorry, I don't have a great prepared answer for sort of ranking things in terms of complexity, but it's definitely worth understanding the different algorithms and what they're doing, so that you can sort of understand why they might be more suited to different problems. Yeah.
It really depends on kind of the problem at hand that you have in terms of like what are data, like you mentioned, those time series analyses you
Yeah.
focus on?
And I would say that like the classic, and this is just Jack Collins talking. This is just the opinion of Jack Collins and not necessarily anyone else. But the typical like machine learners answer to what to do here is that we just try all the models and then we just see what happens. So, you know, the paper that I'm working on has like 2 weeks of computation time required to fit, because I'm fitting recurrent neural networks, but I'm also fitting tree-based models and linear models, and I'm trying all of them with different parameters, and I'm letting some of them have penalty terms and trying different number of layers and neurons and so on and so forth. And when you add it all up, it takes about 2 weeks to run it all. So that to me is a somewhat typical machine learners approach, which is if you can, try everything. And usually we're restricted by the fact that, you know, because that takes a long time and we don't necessarily want to use up too many computing resources, then we try to think about the theories behind things and then sort of try to think about what's worth trying. So we usually use, I think that it's typical to use theory like this to have a guess as to what could be worth trying. But then ultimately you try a lot of things and then experimentally determine what seems to work. So it's a bit of a throwing spaghetti at the wall type methodology, in my experience. Go for it, please.
Yeah, thanks, Jack. I actually have a question about this playground example.
Yeah.
So the way I understand it, right, ratio of training to test data is 50%. That means it's trained on a random 50% subset of these data.
Yeah, that's right.
Okay, then my question is this, like, let's say we didn't have a random training set, but something that's systematic, right? So
Yeah.
if we look at this, we can make sense of this by saying, okay, we have two parallel worlds, right? Outward moving orange world, which starts at the center, so at x0 and x1 at 0, x2 at 0. It's downward moving and outward moving, same for blue, just upward starting and outward moving, right? So let's say we cut off the 50% that are on the most outward edges of these worlds. And the prediction problem is essentially one of extrapolation, right? If we look at this, we see this would be pretty poor, because everything that's outside of the data that we currently have, and which is in the upper half, is orange, and everything that's in the lower half is blue. So is there any way to fix that?
Absolutely not.
Okay.
Not like in my opinion, you know, there's data scientists in the world who are a lot smarter than I am, and maybe they've got another opinion. But what you're getting at is this idea that you and I can visually discern this pattern. You and I can just visually take a look at these at this shape, and if you know, one of us was to take an eraser and just rub out the dots in the middle, you and I would still be able to look at it and reason that this is the rest of the pattern that's been removed. But the model is only going to take a look at is fitting to data that it has got. So I can't actually do this with the tool that I've got here, but I imagine that if you just rubbed this out, it would basically just either make that region one color or the other, which is completely incorrect, or it would make it, you know, white. It would have it in the 50-50, I don't know category. But either way, that's not quite. Either way, it's just not getting it right. So you're completely correct that if it just doesn't have data from which it can, if the data in the training cases aren't similar enough to what you're giving it in the test cases, it's not going to make good predictions, at least not with this setup. So I like to think of this as there's a difference between being able to construct a model that predicts something really well and understanding a system, right? There's a difference between ancient Romans being able to figure out that if you build a bridge this particular way, you get a really strong bridge that can hold lots of weight, and having Newton's 3 laws of physics and deep understanding of material science on a molecular level, right? There's a difference between understanding what's actually going on and constructing a model. And machine learning models typically don't provide like an understanding of the underlying system. They provide a pretty good means of making predictions. And if you can figure out what's happening in a system from these weights and biases and neurons that make up the predictive system, then you're doing really well. But you know, it's not guaranteed. A good example of that is like weather prediction algorithms. Like most weather prediction algorithms are not machine learners. They're actually like physical simulations of trying to actually get the idea of what's happening in the atmosphere and trying to model what's really happening in the atmosphere and then guess what's going to happen next to the atmosphere. But they're not stochastic, or well, they are statistical models, but they're not machine learners in the sense that they were trained on data and then they're making predictions only on the basis of what they saw in training.
Would it make sense to frame this then as a reasonable predictive performance in terms of interpolation, but a rather poor performance in terms of extrapolation, in the sense that you can learn something about hypothetical cases within the range of your features,
yep,
but not outside the range of your features?
That's a good way to put it. And the other way that we talk about is something called domain shift. And domain shift just refers to how different what it is you're applying your model to, or you're testing your model on, is to the data that you trained it on. An example could be, so one example I'm looking at now is, what if we trained a model on one panel survey and then applied it to a totally different panel survey? And obviously there's going to be big differences, even if we've got comparable things like people's ages and incomes and so on, but the distribution is going to be a bit different because they're totally different people. So you would expect that a model that is being applied to data it wasn't trained on is going to do a lot worse. At the same time, maybe it won't do so bad. So for example, we could train a model that guesses whether an email is spam based on the words that are in the email. And we train that model and then we hook it up to everybody's email inbox to do the automatic spam detection that we all have on our Microsoft Outlook inboxes. But over time, spammers are going to maybe start to use different language, say, for example, and then maybe it's not going to do so well. So then we start to take a look at how our model's performance might be decaying in the real world over time, and then say, oh, the domain has shifted a lot. We need to retrain the model on new data. But yeah, the problem of if you're applying your model to data that's totally different to what you trained on and it does lousy, I'm not aware of a solution to that.
Do we have any more questions online, maybe? Yeah, that's just me encouraging everyone to ask questions. Okay, should we wrap this up? Okay, thank you again so much for doing this here today, Jeff.
Yeah, thanks for having me.
Super insightful. Do feel free to check out Jack's tutorial on Method Spites, which gives you all the details on what he talked about today, as well as all the Python code. And we will be back in a month from today on November 15th, same time, same place, with a talk on infrastructures for finding, accessing, and reusing research data in the form of the University of Mannheim Library Research Data Center and BirdEd and FDI by Irene Schum and Ulrich Krieger. Thank you so much for being here today, and we hope to see you next time. Bye-bye.